Hello everyone, my name is S. Jawahar Reddy. I am from Information Technology branch, A section, and my roll number is 20951A1229, and my topic is Amortized Analysis, and the subject is Design Analysis of Algorithms, and I am from Institute of Aeronautical Engineering College. So, what is meant by amortized analysis? So, amortized analysis is used for algorithms where an occasional operation is very slow, but most of the other operations are faster. In amortized analysis, we analyze a sequence of operations and guarantee a worst case average time that is lower than the worst case time of a particularly expensive operation. So basically what we do is uh, occasional operation is very slow. If the occasional operation of an algorithm is very slow, but most of the other operations are faster. In amortized analysis, we analyze a sequence of operations and guarantee a worst case average time that is lower than the worst case time of a particular expensive operation. The example data structures whose operations are analyzed using amortized analysis are hash tables, disjoint sets, and split trees, etc. So, hash tables, disjoint sets, and split trees are the data structures whose operation are the operations data structures which are analyzed using amortized analysis. Amortized analysis is used for algorithms where an occasional operation is very slow but most of the other operations are faster. In amortized analysis, we analyze a sequence of operations and guarantee a worst case average time that is lower than the worst case time of a particularly expensive operation. So let us consider an example, a simple hash table insertions. How do we decide on the table size? There is a trade-off between space and time. If we make hash table size big, such time becomes slow, but the space required becomes high. uh, Let us consider a hash table. Simple hash table insertions. How do we decide on table size? So there is a trade-off between space and time. So there is a trade-off between space and time. If we make hash table size big, such time becomes low, but the space required becomes high. So this is the example of simple hash table insertions. So the continuation is the claim the claim that hash tables have big O of 1 expected performance for lookup and insert is based on the assumption that the number of elements stored in the table is comparable to the number of buckets. So if a hash table has many more elements than buckets, the number of elements stored at each bucket will become large. For instance, with a constant number of buckets and big O of n elements, the lookup time is big O of n and not big O of 1. The solution to this problem is to increase the size of the table when the number of elements in the table gets too large compared to the size of the table. If we let the load factor be the ratio of the number of elements to the number of buckets, when the load factor exceeds some small constant, typically 2 for chaining and 0.75 for linear probing, we allocate a new table, typically double the size of the old table, and rehash all the elements into the new table. This operation is not constant time but rather linear in the number of elements at the time the table is grown. The linear running time of a resizing operation is not as much of a problem as it might sound, although it can be an issue for some real time computing systems. If the table is doubled in size every time it is needed, then the resizing operation occurs with exponentially decreasing frequency. As a consequence, the insertion of n elements into an empty array takes only big O of n time in all, including the cost of resize. We say that the insertion of operation has big O of 1 amortized runtime because the time required to insert an element is big O of 1 on average, even though some elements trigger a lengthy rehashing of all the elements of the hash table. It is crucial that the array size grow geometrically, doubling. It might be tempting to grow the array by a fixed increment, example 100 elements a time, but this results in asymptotic linear rather than constant amortized running time. So let us see the continuation. Amortized analysis is a worst case analysis of a sequence of operations to obtain a tighter bound on the overall or average cost per operation in the sequence than is obtained by separately analyzing each operation in the sequence. For instance, when we considered the union and find operations for the disjoint set data abstraction earlier in the semester, we were able to bound the running time of individual operations by big O of log n. However, for a sequence of n operations, it is possible to obtain tighter than an big O of n log n bound, although that analysis is more appropriate to 4820 than to this course. Here, we will consider a simplified version of the hash table problem above and show that a sequence of n insert operations has overall time big O of n. There are three main techniques used for amortized analysis. So the first one is the aggregate method, where the total running time for a sequence of operations is analyzed, and the second one is the accounting or bankers method, where we impose an extra charge on inexpensive operations and use it to pay for expensive operations later on. And the third one is the potential or physicist method, in which we derive a potential function characterizing the amount of extra work we can do in each step. This potential either increases or decreases with each successive operation but cannot be negative. So let us see the points on amortized analysis. Amortized cost of a sequence of operations can be seen as expenses of a salaried person. The average monthly expense of the person is less than or equal to the salary, but the person can spend more money in a particular month by buying a car or something. In other months, he or she saves money for the expensive month. The above amortized analysis was done for dynamic array. Example is called aggregate method. There are two more powerful ways to do amortized analysis called accounting method and potential method. We will be discussing the other two methods in separate course. The amortized analysis doesn't involve probability. There is also another different notation of average case running time, where algorithms use randomization to make them faster, and the expected running time is faster than the worst case running time. These algorithms are analyzed using randomized analysis. Examples of these algorithms are randomized quicksort, quick select, and hashing. We will soon be covering randomized analysis in a different course. So amortized analysis of insertion in red black tree. Insertion in a red black tree. Let us discuss the amortized analysis of red black tree operations using the potential method. To perform the amortized analysis of red black tree insertion operation, we use the potential or physicist method. For the potential method, we define a potential function phi that maps a data structure to a non-negative real value. An operation can result in a change of this potential. Let us define the potential function phi in the following manner. let us go to next slide. So this is the potential function g of n equal to 0 if n is red, g of n equal to 1 if n is black with no red children, and g of n is 0 if n is black with 1 red children, and g of n is 2 if n is black and has 2 red children. So this is all about amortized analysis. Thank you.